This is a lecture on kinetic energy. It says, I like to move it, with moving being the key to all kinetic energy. It says, all change is not growth, as all movement is not forward, by Ellen Glasgow. So let's take a look at kinetic energy with our learning goals. So it says, first, you should be able to identify the factors that determine kinetic energy. So what is required for kinetic energy to be present? You should be able to relate work, which we learned in the previous lesson, to kinetic energy, which we're learning in this lesson. And you should be able to use the formulas Ke equals 1 half mv squared and W equals delta Ke. So let's go ahead and take a look at our first topic. And it says, let's get moving. So this is the experiment that you've already done. In the experiment that you've already done, you put a hanging mass over the edge and you had it pull the car through the gates. And the whole purpose of this was to say, okay, I'm applying a force because this thing right here is exerting a force. It's pulling this car with that force F, and it's pulling at a certain distance between the photo gates, or D. So you had this FD term. In other words, you calculated the work that you were exerting on the car. And what you did is you actually used these photo gates to figure out what the velocity was here and what the velocity was there. You also knew the mass of the car. So inadvertently, what you were doing is you were proving our first theorem by saying that the force times the distance was actually equal to the change in what we call the kinetic energy. It allows you to predict it. And conservation of energy is the reason why. No matter what you do, energy must be conserved in a closed, isolated system. And you say, well, wait a second, I actually found a little bit of difference. Yes, you found a little bit of difference because of something that we call friction that we did not account for. Now, we tried to reduce it as much as possible, but you're still going to see a little bit of discrepancy between the two. Realistically, the conservation of energy occurs in this system. So it says the work must equal the change of another type of energy. We said the velocity increased, so since the velocity increased, we say kinetic energy. And this is called the work energy theorem. I like to call it the work kinetic energy theorem because it's dealing specifically with kinetic energy. And what it says the amount of work that you do is equal to the change in kinetic energy that an object will have. And it makes a lot of sense. If you have a car that is at rest, because it's out of gas, and all of a sudden it starts to move, the only reason it starts to move is because there's somebody behind the car actually pushing the car. Whenever you push the car, you're doing work on it, and as a result, it changes velocity. So, this delta Ke, first of all, anytime you see the term delta, remember that means change. So in our case, delta Ke stands for the change in kinetic energy. It is an energy. Just as all energies are measured in joules, this one is measured in joules. The kinetic energy cannot be measured directly. It's got to be a combination of two measured things. So because of that, we say that it is actually calculated, just like work is calculated. So let's take a look at this first one. It says, example A1, what is the final kinetic energy of a car when a net force of 100 newtons is exerted on a car initially at rest over 25 meters. So you are looking for the final kinetic energy. Okay, so I'm going to say Ke, and I'm going to put a little F here just to say that it's final. Okay, we are given the net force. We are given the distance, and we're also actually given this right here, this rest term. So if you were to look, I could say the force is equal to 100 newtons. You could say that the distance was 25, and we are trying to solve for the final kinetic energy. So our equation is work is equal to the change in kinetic energy. Now remember, for anything, the change in anything is always the final minus the initial. So Ke final minus Ke initial. So we can say work is equal to Ke final minus Ke initial. And in this case, work is force times displacement. So you have your equation in an expanded out version. So I can do force times distance, or 100 times 25 is going to equal Kef minus, and then you get stuck here like, but I don't know the initial kinetic energy. Kinetic energy, remember from the first presentation, is the energy of movement. When an object is at rest, it is not moving. Therefore, it has zero kinetic energy to begin with. So what I can say now is that the final kinetic energy that an object has is equal to 2,500 joules, which is the work that was done on the car to begin with. The next example says sketch the shape of a force versus change in kinetic energy graph. Okay, whenever you're sketching the shape of a graph, you always want to start out with the equation. So the equation that we have here is W equals, W equals delta KE. And you say, okay, well, my equation doesn't actually have anything to do with that because I want to know about force. So we will expand it out to force times displacement equals change in kinetic energy. Okay. And you say, well, that's not particularly helpful here because I've still got this distance term. Remember, whenever you are looking at a graph, it has to be between two variables. It is understood that you say that the second variable is constant at this point. So this right here, this d term, is going to go ahead and just go away. It's still there, but it's not going to be a part of the graph because we're going to consider it to be a constant. So since it is constant, we can now take the equation F equals delta KE. In fact, it's not really good to say an equal there. We'll say it's proportional to because it's not equal to each other anymore. But we're saying they go up together. Now I need to decide which one of these is my x variable and which one is my y. Remember, on the x variable on the x-axis is the one that you change in an experiment. And you can change the force that's exerted on an object, and as a result, there is a change in kinetic energy. So force would go on the bottom, and we would put force in newtons. Okay, on the left, we would put change in kinetic energy, and we would put joules, and that would be on the left right there. So now we look at our equation. So this right here is an x value, this right here is a y value, so you can kind of set it up like that. What does a y equals x graph or an x equals y graph looks like? It is a linear graph. So what you're saying, that's a terrible linear graph, it's a straight line graph. So as a result of the straight line graph, you're saying with every doubling of the force, you're doubling the change in kinetic energy. With every tripling of the force, you're tripling the change in kinetic energy. So it's a direct relationship. This one says you have a 1200 watt motor that operates at full power to accelerate a 500 kilogram car for 8 seconds. So when you do this, it says what is the change in the kinetic energy of the car, and then it says assume the motor is 100% efficient. So we are trying to figure out what the change in kinetic energy is. So if we look at what we've got, we have a power because it's a motor and it's 1200 watts. We are trying to accelerate a 500 kilogram car for 8 seconds. And it says, what is the change in kinetic energy? Okay, so if we look at our equation, our relationship between work and change in kinetic energy is W equals delta KE. Now, I don't exactly have the power, so I need to look at another equation, and I need to know where to go. If you look, power is a key here. I'm going to somehow have to put in power equals work over time into this equation. And if you look, I want to be able to rearrange it for something else. And if you look, I can say I can multiply both sides by t. And when I do that, I get work equals power times time, which is great because I can substitute that in here and I can now say power times time is equal to the change in kinetic energy. And if you look, I have power and I have time. So I can substitute those in there and I can say, okay, 1200 times 8 equals change in kinetic energy. Whenever you multiply that out, you would get like 9600 joules would equal my change in kinetic energy. And people say, but wait a second, you didn't do anything with 500 kilograms. Remember, There are cases in which you're going to be given too much information. The information is meant for you to try and expand it out. I could have asked you to find the acceleration in this particular case, and that way you could have used that, but it's irrelevant for this particular question. And you need to be able to recognize and say there's something that I don't need here.